All right, guys, welcome back. We are back on into our BGP topics. Still talking about those BGP attributes for our decision tree that BGP uses. And we're actually getting kind of down to the last part of BGP here, but we're going to be talking today about traffic engineering with ASPath and multi-exit discriminator. And then after that, we should actually wrap up BGP next week. With these discussions, and then we really only have optimizing routing, and then we're going to get into some MPLS stuff as well. So we're getting down to it. We'll probably add a few topics as well based on some of the blueprint topics that we may not have covered at this point. So we'll take a look at some of that stuff as well. But for now, we're working with this topology here, our same topology that we were working with before. And we're going to look at BGP traffic engineering in this case with ASPath, which we've actually already seen an example of, and multi-exit discriminator. But keep in mind, this is the opposite direction of what we saw in our previous exercise where we talked about weight and local preference. So typically these attributes are going to be set outbound in order for us to influence out, if you will, the inbound traffic and path selection process. Keep in mind that this is only a suggestion. This is not something that we can actually enforce, because we can only technically enforce how we decide to route out of our autonomous system, and we can make suggestions on how to route into our autonomous system. All right? But there is kind of a unspoken rule of, hey, if you're going to send me these attributes, then I'm going to try and honor them as best as possible. Okay? Now, if I go back to my list here of our attributes, we're talking about specifically MED, multi-exit discriminator. This is type code number 4. This is an optional non-transitive attribute, which means it gets sent to the neighbor, it gets sent to the peer, but it does not get passed beyond the peer. We'll actually talk about part of that concept a little bit later on when we get into towards the end of the lesson for tonight. Okay, and then also ASPath. ASPath is type code 2, and that's a well-known mandatory attribute, meaning that everybody needs to understand it, everybody needs to know how it works, and we also have to kind of include it as part of one of the core elements in the BGP selection process. Now, if I look at the actual list, the decision process, ASPath actually falls in at number 4 in the list. So pretty much after weight and local preference is what we talked about in our previous lesson. And then further down, we have our multi-exit discriminator, which is option number 6. Again, ASPath can be applied inbound or outbound, but typically outbound. We're trying to influence how our peers see our network. And then as those prefixes are propagated from one autonomous system to the next, the ASPath attribute collects all of the path information, and then we can manipulate that value, essentially making the path longer, artificially longer, to affect path selection overall. Okay? And we'll see how we actually manipulate this with route maps and ASPath access lists. As far as the multi-exit discriminator, by the way, shortest path preferred with ASPath. Multi-exit discriminator, we prefer the lowest value. It's also an outbound policy. There is no option for inbound MED in this particular case. This is, like I said, just a suggestion that we're sending to the peer, and that suggestion is essentially, hey, this is how I would like you to route, but it's not necessarily guaranteed, right? And the lower number is better. We also manipulate this with route maps, and the peers can choose to either ignore this suggestion or to accept that suggestion. So that's what we're going to talk about, all right? Because the multi-exit discriminator is a non-transitive attribute, that means that the provider itself or your peer that you're peering with is not going to pass it on. It's not to say that they can't reset it if they want to. We could continue to reset it on the edge, on an edge-by-edge basis if we wanted to go ahead and propagate that information. But MED is one of those kind of not so easy attributes to work with. There's a lot of complicating aspects to MED. And we're going to come back to that later in more detail. But here we're just going to look at it from a general path selection perspective, something that we've kind of already investigated previously. In the later sections, we'll take a look at some of the specific differences between, what is deterministic med, how does that differ from, say, always compare med, and so on. So let's take a look at our topology again, just to do a quick review. I'm going to grab a snippet of this as well. And so we can make some notes on this topology here. Pretty much the same topology we've been working with. We've got a couple of peers. Router 1 is an external BGP peer with router 8. AS100 is connecting to AS50. And R5 and R3 are connected to router 7 on AS51. We have multiple links for between R5 and R7, and we've got a single link between R3. Again, in this topology, router 4 is a route reflector, negating the need to have a full mesh full IBGP mesh in AS100. So same topology that we've been dealing with in all of our previous lessons as well. Okay. We looked at local preference and weight before, and just a quick review. Local preference was something that we could send into the AS, which propagated to all the peers, allowing us to make a decision on how we're going to route to external prefixes. Weight was more of a local selection process, so we applied weight, for example, on router 5, applying a weight to this link and this link. For either inbound, well, only inbound prefixes, I should say, because weight is a internal, locally significant attribute. And we could simply apply weight to a neighbor relationship. We could say, okay, I want the weight here to be different than the weight here, so that all the traffic I'm getting from router 7 is going to go over my primary path, and then I'll use that backup path as it's designed as a backup. Okay? So what we want to do now is we want to affect the path selection in the reverse direction. So I'm going to actually come into router 2 here, and we are going to add an additional prefix. Not that we really need to, but we're going to go ahead and do that anyway. 22, 22, 22, and 22. And we're going to propagate this into BGP. So let me go into router 2. Config T, interface loopback 22, IP address 22, 22, 22, 22. 255, 255, 255, 255. And then I'm going to go into router BGP 100, and I'm going to say network 22, 22, 22, 22, mask 255, 255, 255, 255. All right, so I should see that in my database here. Let me just do this, show IP BGP regular expression, and I'm going to do starts with $. And I should see all of the paths that are originated by me, because there's no AS path information, because these are internal routes. Just another example of how we can use these regular expressions to kind of filter out information. Obviously, we don't have a very large database here. Keep in mind on the in the case of the lab, you could see significantly larger outputs. So being able to filter this information could be very useful. So we do see that the 22 prefix is here. It's locally originated. It has no metric assigned, no local preference. It does have a weight of 32,768 because we're originating this particular prefix into BGP. Now, if I go look at router 7, show IP BGP 22, 22, 22, 22/32, I can see that I'm actually originating this prefix into autonomous system number 51 through 4 different paths. Router 5 is advertising this, router 8 is advertising this, router 5 again is advertising this over a different link, and router 3 is advertising this. But I do see here we've got something interesting going on between router 5 and router 7. These are some remnants of some of our previous discussions. So let's take that out, where we were doing AS path prepending. We may end up reapplying it, but I want to make sure that we're seeing this as part of our lesson and part of our discussion in this particular case. So let's go ahead and actually just kind of clean this up and just let the routers make their decisions based on standard processes. So we're going to do take this out, no neighbor prepend out, and we're also going to do no neighbor with the advertised map. That was way back in one of our previous lessons there. So now if I go back to router 7, I don't know if anything would necessarily change. Whoops, I've got to go back to router 5 and do a clear IP BGP star out. Oops, clear IP. All right, now we'll go to router 7 and see if we see any differences here. All right, now as far as the best path goes, it obviously changed in this particular case, but we're seeing, well, we're still seeing a weight applied here. And that's actually probably one of the good things to note is because you know what all the defaults are, because you know what these things should look like, you should be very easily able to identify if some sort of non-standard function is taking place. So it looks like we're applying a weight on router 7 to the prefixes that we're learning over the 75.5 length. So section BGP. And I just want to clean that up because I want to make sure that we're analyzing the data as it should be seen without any kind of manipulation of the path selection process. So router BGP 51. And let's get rid of the wait command there. Let's do a clear IP BGP star in because, why do I keep doing that? Clear IP BGP star in and show IP BGP 22.22.22.22/32. All right, now we're looking clean here. So 3 different things, the path changed 3 different times because of different selection criteria that we were utilizing. But looks like now we've got 4 external sources. Router 8 is providing this prefix through AS50 and then back to AS100. Router 5 is originating this prefix from AS100. And router 3 is originating the prefix from AS100, and router 5 is also originating this prefix over the secondary link, which is the 75.5 link. So that's exactly what we would expect to see. Now, with regard to why we happen to choose this path as opposed to the other paths, we'd have to go through the entire path selection process, and ultimately we would end up choosing this path because of tiebreakers. Because the AS path is the same. This one gets eliminated, of course, because the AS path is longer than the rest. But between these 3, everything is pretty much the same. Same local preference, same origin code. They're all external prefixes. So we chose this particular path based on one of those tiebreakers that come into play when we go down the list. Okay. So if we look at this from router 7's perspective, reaching this 22 prefix, we're selecting the path through router 3. All right, we do have multiple views to the destination, and we can see that those views are fairly straightforward. If I do a quick show IP BGP, oops, what's going on there? There we go. Show IP. Sorry about that. The dog was barking at somebody at the door. All right, so IP BGP, reg expression underscore $100. We can see that these are all the prefixes coming from AS100, and 22 is here. We're actually selecting, to get to the 22, we're actually selecting the path through 37.3. But if you look at all the choices here, right? We can tell we're selecting the path, that third path, because of the greater than symbol. But if you look at all the choices here, there's really not anything here that's going to allow us to make a decision based on some of the standard attributes that we've been talking about, right? Metric is not set, local preference is not set, weight is not set, AS path is the same. even the code that we identify for the origin is identified as IGP. So there's multiple options, but we're choosing the path through router 3. All right. Now the next hops are actually being reset in this case. If this was, because this is the direct peer, the direct eBGP peer, router 7 is actually receiving the next hop information from the routers that are propagating the prefix. If I had some other routers in AS51, then I might have some issues with reachability and route recursion, because the next hop is not going to be reset when I go from an eBGP peer to an iBGP peer. We don't have to worry about that in this particular case. We'll actually see that in the other direction. We're going to inject some prefixes from router 7 going over to AS100. All right. So the thing that you need to understand is, depending on what attribute you're using, whether you're going to use ASPath or MED, you need to define where we set the attribute, on what particular peering we are going to try to set it, and whether or not it's going to be some sort of higher value or some sort of lower value. All right. Because again, because of the different types of attributes that we have, we're not always guaranteed that a particular attribute is going to respond in a particular way, right? Some attributes might be locally significant to the router. Some attributes are propagated throughout the entire autonomous system. So it's really important that you understand how each of these attributes are processed, okay? Now, one of the simple ones that we see is ASPath prepending. We look at all the ingress paths that we do not want to prefer, and we would basically prepend on those particular links. So whatever link that we're prepending, that means the traffic should not be coming in that way, and so on. So let's say we know based on our investigation that we're choosing the path through router 3, okay? But let's say for that 22, 22, 22, 22 prefix that we would go ahead and want to prefer this path. So I'm basically going to try to influence router 7 on how to route to the 22, 22, 22, 22, 22 prefix. I think that was too many 22s. But again, this is not something new. We actually saw this in one of our first BGP discussions about metrics. We simply have to create a route map that matches an AS path, and we simply prepend based on that, prepend different prefixes based on that, or ASs based on that desire, right? So we have peering towards router 7 from router 5. We have peering from router 7 from router 3. And then again, depending on which one we want to manipulate, we're going to enforce the AS path prepending change based on that decision tree or that decision process. All right, it's very, very important though that you understand what the effect is on the overall topology, because we may end up, if we're doing multiple prepending, we're prepending maybe 2 or 3 different paths, we may end up sending the traffic this way because it might natively have a shorter path. So there's lots of, you have to consider every ingress and egress point from the autonomous system when you decide to do this manipulation. All right, so let's go ahead and create a route map. We're going to go ahead and do this on router 3 and router 5, but we have to do it independently kind of, because we're applying it to different peers. So we're going to come into router 3, route map, and we'll just call this out AS100, permit 10, and match. I might have to actually create the AS path access list first. Match AS path 100. Nope, let me do it. Okay. Then I have the option. We still have to create that AS path access list, but set AS path. Now I have several options here, right? I can tag the path, I can prepend the path. On some iOS codes, you might actually even be able to see, you know, something like what was it called? there was an option. I can't think of the name of it, but in other code there might. I think it's the last AS, or I forget what it's called. Let me see if I can Google it real quick. Because that's obviously not what we're going to use in this particular case. Prepend last AS, that's what I was looking for. So there's this option for last AS. We have tag, we have prepend, which we're going to use. We'll talk about the tag later on, actually, get into some of the other discussions. But last AS is kind of the simplest option, because it basically is a shortcut to put a specific number in there. But we don't have that option in our particular case. So we're going to just use the prepend option. Now you'll notice here it's, oh, there it is. I was looking in the wrong spot. So it is here in this code, prepend the last AS. I suppose I needed that prepend option. We'll talk about the tag option, like I said, a little bit later on, and what that tag option provides us in the process. All right. We got the original AS number option. We've got the kind of the modern or extended version of the AS that we have available. We're going to go ahead and prepend just 100 multiple times. We can do it as many times as we like, just depending on whatever our end result is. You can actually technically put any number you want in here, but that's really bad etiquette, right? You shouldn't really prepend somebody else's AS unless your objective is to black hole them from getting to you. Because remember, if I see my own autonomous system number in an update from an external peer, I'm going to ignore that as a loop avoidance mechanism. All right? So technically, we should really be only prepending our own AS. The key here, though, is that the CLI won't actually create an error. All right? Now, keep in mind, we still have to put in our secondary condition, because we still want all the other stuff to work. So out AS 100, and we'll just do a blanket permit 20. Okay, so we go into the BGP process, router BGP 100, and we're going to apply this to our neighbor relationship. Actually, let me do this. Do show IP BGP summary and neighbor. We're applying this to router 7 in this particular case. And we're going to apply the route map. What did I call it? Out AS 100. Out. Okay? Now, you have to be careful with this, because if you accidentally mistype the name of the route map, you may end up actually filtering out all of the prefixes that are being sent to the peer. So make sure that we don't do that. All right. So let's do a clear IP BGP star out, so we can make sure that we're propagating those changes over to router 7. Now we need to do the same thing on router 5. In fact, let me just go to router 3. Do show run pipe. Oops, you know what I forgot? I forgot the AS path access list. Let me check something real quick. Oops, show run. What am I doing that for? Let me see if we're seeing this information in show IP BGP. Yeah, see, we're not seeing the prepending taking place for the prefixes that we're advertising to the peer. And that's because I did not create the appropriate access list. Remember, I referenced the AS path access list. Now, there's a couple of things, there's a couple ways I could do this. I could do this by matching a particular prefix, but in this particular case, I'm just going to apply it to the peer in general. So if I do a show run pipe section route map, we can see that we're referencing a AS path access list, which I didn't create. Naturally, if I'm not identifying how I'm going to apply the filtering, then it's not going to work, right? So this AS path access list here. So let's actually create that. IP AS path access list 100, and we're just going to say anything that comes from this autonomous system. So that would be begins with $, right? So essentially we're saying, okay, for this peer over this link, anything that originates within AS 100, or actually, you know, because it doesn't have an AS applied. Remember, the AS path attribute only gets applied when the prefixes are advertised to the peer. So this would mean all of the prefixes that are originating within the autonomous system. I don't know if I have to clear. Yeah, looks like I do. So let's go back to router 3 and do clear IP BGP star out. So we can re-advertise those attributes. There we go. That's what we wanted to see. All right. So now, again, this is applied. This is applied to all of the prefixes coming from this autonomous system. You could get a little bit more creative, right? And get into a situation where you're applying it only to an individual prefix, and then you would need prefix lists to match a particular prefix. You might have to actually do multiple levels of filtering. But I'm just going to kind of keep it simple in this particular case. Okay. So already R7 should be making a different decision than it was previously. Previously it was going to router 3. Now we can see it's going over the 57.5 link. If we look at our topology here, that is this link here, but remember we said we wanted those prefixes to route over this particular link here. So again, we can do the same thing. Go into router 3, do show run pipe section access dash list pipe route map pipe BGP, and we should be able to pull all this out here. So let's go ahead and grab our access list. Let's see, IP access list. All right, let's go to router 5, config T, paste that in there. And our route map. All right. And we could even get a little bit more creative here if we wanted to, where we could prepend, actually even more prefixes or even more autonomous system AS path information to the route to have a hierarchy of choice, if you will. But in this case, we're not going to do that. All right. And then we're going to go to router BGP 100. All right, and we're going to apply this. At this point, I just need to type it in. All right, we want to apply this to the peering relationship on 75. So neighbor 172.16.75.7 route map out AS 100 out. And do a clear IP BGP star out. All right. So now previously we were using the 57 link. And I think I applied it to the wrong one. I actually wanted to force it to take the 75 link. But that's okay. We can still see that the policy is applied, right? Because I should see for that 75 link that the AS path was prepended. All right. Ken has a question here. Let's see. If you were doing this in a production network, would you use the AS path prepend as opposed to other options like weight or route maps, prefix lists, etc.? I'm going to split that up in a couple of different answers. First of all, with regard to Dorian in Virginia, I have no idea. Haven't gotten any notification that my flight is delayed, so we'll see. Tim would be able to answer that, though. He's kind of up there. I imagine it's probably just a little rainy. But So if I was doing this in a production network, we have a lot of different options with regard to whatever our goal is, right? We can choose weight, we can choose local preference, and AS path, again, it's a matter, the question you have to ask yourself is, am I trying to influence my inbound policy or am I trying to influence my outbound policy? That's what you really need to ask yourself. And that alone, that question alone will direct you to the types of attributes that you're going to manipulate based on how they get applied to your peering relationship. Once you've answered whether or not it's going to be an inbound or outbound policy, AS path, for example, could be both, you need to identify essentially what is my view of the topology, because AS path is something I could apply to an internal peer. I can't propagate AS path information. I can't do AS path prepending to iBGP peers, but I could certainly influence my iBGP peers by adjusting the AS path length at the perimeter. So there isn't a specific answer with regard to what's better, right? It really depends on answering several questions. And I think the most important question is there's two really important questions. First question you always ask yourself, is this an attribute that is going to be used to influence my outbound policy or my inbound policy? The second question you ask yourself is this an attribute that needs to propagate to all of the peers so they have a similar view of the topology, or is this an attribute where only the local router is concerned? Because then you're still talking about choosing a different type of option. Right? A weight, for example, is only locally significant to the router, whereas local preference would propagate through the entire autonomous system. Wouldn't propagate beyond the autonomous system, but it would propagate within the iBGP peering relationship. And then you also have to ask yourself, how is the iBGP cloud look? How does the iBGP domain look? Is it, am I using confederations? Am I using a route reflector? Because that alone will change essentially how everybody views that topology within that autonomous system. So it's a lot of different questions you kind of have to ask yourself. Now, with regard to route maps or prefix lists or AS path access lists, those are just ends to or means to an end, right? Typically prefix lists, typically with BGP, whenever you're doing any kind of manipulation, it's going to have some sort of route map applied to it, without a doubt. Because we want to match certain conditions and we want to set certain conditions. It's kind of rare. Actually, I wouldn't say it's rare. It's actually pretty common, but to go ahead and apply a weight or a local preference or whatnot to appear in general, because that's going to affect all of the prefixes that I'm learning from that particular peer. Whereas if I'm using a route map, I can match specific conditions. If I'm only concerned about matching prefixes, not prefix length, I can use an access list to match. If I need to match a prefix and a prefix length, then I might use a prefix list, and so on. If I'm matching AS path, I'd have to use an AS path access list, and so on. So it's a challenge. It's a challenge to decide how you're going to do something, because in essence, it changes. It changes pretty significantly depending on what your answers to those various questions might be. All right. So hopefully that at least gives you some idea. All right. So we've done the prepending, right? And we've obviously seen the result of that based on what we see on router 7. All right. Like I said, you should only prepend your own AS, not other ASs. All right. Now we see from router 7's output here that we have long path lengths. We have to consider which router to apply this on. This is kind of what I was just talking about and what that effect is going to be. You want to make sure that you're not learning about a path from iGP between two different ASs. In this case, we're not, because we're not advertising the peering links between the peers through IGP. All right, but remember, ultimately it's the RIB that does the route recursion process, and the routing information base is what's going to make that routing decision. We didn't have to in this case. It's performing as predicted, but you may have to walk through the process and identify how the route recursion is working. And you might actually have to take into account more than just the BGP attributes, because BGP just says you're going to go this way or that way, But that doesn't mean that that's the way you're actually going to route, because the recursion process could be different, right? I might be relying on an underlying IGP routing process to make a decision, and BGP is saying do one thing, but IGP is trumping that decision and doing something else. All right. Additionally, as you make these modifications at different points in the topology, inbound, outbound policies, and how the BGP interacts with the IGP process. So the other thing to consider is be careful about creating these looping conditions. Because if the underlying IGP and BGP don't agree, that could be something that happens very easily. All right? The way we actually verify this is we don't look at the actual BGP information. We look at the traffic flow. We use pings, we use trace routes, we use show IP Ceph and so on to really kind of walk through that recursion process that would take place in a normal operation. Okay? All right. That's basically it for prepending, right? You prepend out the connection you don't want to use in return. So let's look at this in the reverse direction. All right. Let's say in the reverse direction, routes going from R7 into AS100. So I'm going to go to R7, and I'm going to create a loopback 77. And we'll put an IP address 77, 77, 77, 77. And we're going to go into router BGP 51. I believe that's the ASN for that. Yep, 51. And we're going to actually put that into BGP. I think it's already going to be there through redistribute connected, but I'll just go ahead and throw it in here as a standard origination. Okay. Show IP BGP. Begin $, oops, regex. And 77 is in there as a locally originated route. Okay. So we analyze those attributes. Let's take a look from router 4's perspective. Since router 4 is the route reflector in this particular case, I'm going to do a show IP BGP 77, 77, 77/32. And let's see how router 4 looks at this from its perspective. So it says, hey, router 5 is advertising this prefix. It's coming in over the 57 link. Router 3 is advertising this prefix. It's coming over to the 37 link, which is kind of interesting because if I go to router 5 and do a show IP BGP 77, 77, 77, 77/32, I can see in this particular case that I actually have 3 sources. It's coming from router 7, and router 4 over the 37 link. What's interesting about this concept, okay, and this is where, again, you have to kind of walk through the process so you can understand the decisions that BGP is making. Router 4 only knows about one path from router 5, and that's because router 5 chose the path. It chose this as the best path, 57.7, okay? And that ends up being the only path that gets advertised over to router 4. Sorry about that. That ends up being the only path that gets advertised over to router 4 because that's the path that router 5 chose. So we're not actually, we're kind of hiding the topology, if you will, in this particular case because of the fact that we have a route reflector and route reflector clients configured. All right. It doesn't really, well, actually, I was going to say it doesn't really affect our decision, but we still need to consider who we're trying to affect with regard to the decision process. Now, if we look at the topology in this case, we went in our original implementation, we were prepending here, we were prepending out here to kind of, well, that was the idea anyway, we did it backwards, but to kind of get router 7 to take this path to get over to 22. What we're doing in this case is we're going to be using multi-exit discriminator we're going to set a med value out these different links here. Oops, not that one there, to influence how these guys decide to go into that autonomous system. Now you're going to find, well, actually I'll save that revelation for a little bit here, that setting the med value on all three links isn't necessarily something that's going to be very useful, and I'll explain why in a little bit. Okay. So if we're learning about a path through iBGP, we're learning about a path through eBGP. We always prefer the eBGP path because it's not in my own autonomous system. And you know, as I was mentioned before, AS path prepending, we can't really prepend to an iBGP neighbor. So we're going to look at a different option here. All right, so we're going to try the med value. We already know that router 7 is choosing, let's go back to router 7 here. Router 7 is choosing 77, actually I want to go to router, let's go to router 4. All right, well that's the same one up there. So router 4, which is the route reflector in autonomous system number 100, is choosing this path over this path. Right? They have the same AS path length, they have the same metric, the same local preference, and so on. So let's see if we can somehow manipulate this so that router 7, these routers make a different decision on how to get over to 77. All right, so the first thing that we're going to want to do on router 7 is we're going to go ahead and create a prefix list. Sorry about that. Config T, IP prefix list, 77, permit, 77, 77, 77, 77 / 32. So that's an exact match. We're going to create a route map, and I'm going to say to R3 in this case, R3, permit 10. And let me go back to router 4 real quick. Router 4 is going over to router 3. So I want to make router 3 less preferred, just so we can see that influence to router 3. Again, this is where it matters, right? That you understand what these attributes do, what's better, what's worse, and so on. So we're going to match IP address prefix list 77. And we're going to set the med, or the metric, excuse me. We use the term metric in this case. We're going to set the metric to 200, which is actually a higher value as opposed to a lower value. Okay? And then we're going to do our route map to R3. And we're going to say permit 20. That's going to go ahead and take care of the rest of the prefixes. We'll just leave those alone. And then what we're going to do is we're going to set create a route map to R5, and we're going to say permit 10. Now technically we don't really need to set it on both sides. Match, well I can just do this, and let's set metric to 50. Technically we don't really need to set the other one lower. As long as the other one is higher, it should automatically assume it's lower because it's the null value. The null value is 0 anyway. All right. So the last step then is to go ahead and apply this to the peers. So do show IP BGP summary. Pipe include 172. All right, and router BGP 51. Neighbor. Let's see, 172.16.37.3, route map to R3, out. Again, this is an outbound policy. And then neighbor, let's set it on our primary link. Actually, I want to see if the null value is going to affect our decision process. I believe the null value is just simply going to be ignored. And if physically, when we set the value, it should be utilized. But So let's go ahead and apply this router 5 policy to the 57 link. Okay. So neighbor 172.16.57.5 route map to R5 out. Do clear IP BGP star out. All right, so let's go back to router 4 and see what we see. Okay. Well, that's kind of what I expected to see. Unless I mess something up. I'm actually not seeing the prefix from router 5 or router 3 anymore. I'm seeing it from router 5, but the metric is 0. And this is that little moment that I was talking about, but let's see why we're not seeing it from router 3. Show run pipe section, route map, pipe, BGP. I might have mistyped something in the neighbor statement, because I should still be seeing 2R3 out, 37.3. That's good. Let me go to router 3 real quick. Do show IP BGP. So I am getting it here with 200. And on router 5, show IP BGP, I am getting it here with 50. So the first thing I want to see is which path is this router selecting, and that's exactly what I expected to happen. Remember, the default MED value is 0. So what is that telling me here? That's telling me...
Scott.
Yes, sir.
Was there a permit statement for router 3?
Let me check real quick. You know what? That may be what I'm missing here. Yes, there is right here. To router 3, permit 20.
Oh, okay.
Yep. So there's my route map to router 5. There's my route map to router 3. So that looks good. This is actually related to what I was going to tell you guys anyway. And this goes back to what Ken was asking about. Where do I do this? Where do I apply these values? And so on. All right. And this is the challenge with this particular topology. Because remember, MED is a non-transitive attribute, which means that it gets advertised to my direct eBGP peer, but it's not going to be propagated to my iBGP peers. So when I go to router 4, I'm not seeing that metric set because it's an attribute that doesn't get passed between iBGP peers. Let me do a show IP BGP. And yeah, we're only seeing one path. Now, that's the curiosity here, because router 3, let's see how router 3 is deciding. So it looks like what we've got going on here is router 3 is saying, you know what, I'm going to go to router 5 to reach that destination. Which makes sense actually, because that 75 link, which is that backup link, has a MED of 0. So it's automatically saying I'm going to go ahead and choose to go to 75 because I'm getting a MED of 200 on this path, which means that the 75.7 path is going to be preferred. It actually has a local preference of 100 as well, whereas the other path has no local preference. That's actually probably what would be selected first anyway, over MED, because weight and local preference are the first two options. So not everybody has a complete or a common view of the topology. And what ends up resulting in this is if I go over to router 2 and I do a trace route to 77, 77, 77, 77, and I source that from loopback 22, I'm going over to router 1, then I'm going to 4, then I'm going to 1, then I'm going to router 1 and router 4, then I'm going to 3, then I'm going to 7. So there's some kind of strange routing happening here. I'm kind of almost kind of load balancing between router 1 and router 4. which is that's not normal behavior. So you can see it's kind of flapping back and forth. Essentially what's happening in this case is one router is changing its decision on how to reach that destination, and that's propagating through the route reflector into the rest of the domain. All right, MED is a challenging one because of the nature of the attribute itself, because it's non-transitive, because it only goes to eBGP peers. You need to make sure where you're going to apply it. It has to be applied to the right router and so on. So I guess the question would be here then, how could I influence this? It probably wouldn't be my best choice in this particular case because number one, I have a route reflector in my design. That's number one. And number two, I've got these multiple peers that I'm trying to send this prefix information over to. But unfortunately, because router 7 is the one trying to influence the path selection, it has no control over how AS100 decides to route that particular traffic. All right, I doubt you'll see something this complex on the lab that they'll probably get into, but just something to keep in mind. All right, the attribute itself doesn't actually mean that's the way we're going to forward traffic. We have to look at the association of the next hop, how IGP recurses to the next hop. The MED, being a non-transitive attribute, is only compared when it's coming in from the same autonomous system. We don't actually have that problem in this case. We set the MED to 200 on this link. We set it to 50 on this link. Let's go ahead and shut down this backup link, the 75 subnet, and see what happens in this case. Show IP interface brief. Include 75. Do. And that's gig 03. Not that word. All right. All right. So now let's look at it from router 4's perspective. Actually, let's just do our trace route again. All right. So now it's going to 4, 5, and over the 57 link to router 7. If I do a show IP BGP 77, 77, 77, 77, again, I'm not, well, actually I am getting the metric value here, which is another interesting concept, because this also happens to deal with specifically the fact that we are using a route reflector in this particular design. If this was a standard iBGP peer, I would not see that information. So it is saying that I'm actually going to go over the 57.7 link. I got this information from router 4. Because router 4 is a route reflector, I'm going to see that information. If I do a show IP BGP, I'll only see one path to that 77 subnet because I'm essentially hiding that topology from router 4's perspective. Let's go to router 4 and look at it from router 4's perspective. Show IP BGP 77, 77, 77.77/32. So again, we're choosing the path through router 5 because of that metric value, that metric of 50. Okay. It's an interesting concept. I mean, we're still getting the path from router 3, but router 5 is making the decision to go over that. Router 4 is making the decision to go to router 5. It's not going to populate any information from router 3, especially because router 5 and router 3 are making the same decision. They're both going to router 5. All right. So that's pretty much it for this lesson. In our next lesson, we'll talk about some additional manipulations with communities. That's going to be kind of a unique discussion, a little bit different than just simply manipulating attributes. And then we'll get into some BGP route aggregation and traffic engineering with aggregation, leaking out prefixes and whatnot, if you will, and so on. All right. All right, guys, we'll see you guys in the next lesson, which will be Monday night.